Okay, welcome to week 2 of Stars and Galaxies. I left you last time with a little exercise to look at the Doppler motion figure of the granulation motion that was in the last lecture, to get a feel for how fast the convection motion is moving, and that we can probe with the Doppler shift. So if you look at that diagram that showed the magnitude of the velocities coming towards us and away from us, then the typical size, order of magnitude at least, for those Doppler shifts was around about 1 kilometer per second. Maximum went up to about 2 kilometers per second on that diagram. So just taking a number anywhere within a factor of 2 of that range is fine to get an estimate here. That's all we're interested in, is an estimate. There's not really a right or wrong answer. And I said that a typical bubble of gas that's undergoing one of these convective motions would travel about 300 kilometers before it dissolves and reforms or gets to the surface. So that hopefully is a simple calculation. So the time taken to travel a distance d, moving at a speed v, is just dividing the distance by the velocity. So you put everything in SI units, so you've got 300 kilometers here, and 1 kilometer per second here. And so dividing those two is going to give you 300 seconds, or about 5 minutes. Okay. So hopefully that gives you a feel for sort of how fast things are changing there on the surface of the sun. So this whole thing is bubbling over on those kind of time scales. Okay, so let us now move on to today's topic, which is the solar activity. So we started moving, from inside of the sun to the visible surface of the photosphere up into the corona. So today we want to focus on the activity happening sort of in and around the photosphere and the corona. So that will lead us first to talk about sunspots, then to talk about the cycle of sunspot behavior, and then we'll try and pull all that together in a model that attempts to sort of broad brushly explain how all of this activity works. So, unlike the previous picture of the sun I showed you, which was devoid of any sort of visible imperfections on the surface, then this is much more like a normal picture of the sun, where you have these darker regions here that are called sunspots, okay, for a fairly obvious name. Okay, so you can see them all over here. So they come in, this is a sort of fairly big group, but you can see quite a few smaller ones here as well. And these have been known for thousands of years. So even ancient astronomers, especially Chinese astronomers, if you can view the sun, obviously, like I said, normally you shouldn't look at the sun at all with your naked eye or any optical device. But if you do happen to view the sun through a partially thick cloud or a low mist, and that's how ancient astronomers observe the sun, then you can then see these dark spots on the visible surface if the cloud or mist is enough to reduce the glare so that it's safe to look. But again, I wouldn't advise trying that yourself. Okay, so that's what a sunspot looks like. You can see there's a dark region in the middle, which is called the umbra, and then a grey region around the outside, which is called the penumbra. So why do they appear dark? So sunspots appear dark because they're basically cooler than their surroundings. So recall last time I said the photosphere, the sort of yellow disk of the surface of the sun, the visible surface, has a temperature of around 5,800 Kelvin, whereas the sunspots are a couple of thousand degrees cooler than that, around about 4,000. And because the gas is cooler, it emits less radiation and therefore appears darker. So it's really a contrast issue. If you could see a sunspot by itself against the black backdrop of space by itself, it would still be shining very, very brightly, because 4,000 Kelvin is still very hot. But because it's a couple of thousand degrees cooler than the surrounding regions, the visible contrast just makes it appear dark. So that's the explanation there. Now, Sunspots are quite useful in many other regards, quite fun in many regards. They also are quite handy at revealing that the sun rotates. So just like the Earth rotates, the Earth rotates every 24 hours, the sun also rotates quite a bit slower, about once a month. But it also rotates in a very different way to a solid planetary body like the Earth. So the sun, because it's a ball of gas, does not have to rotate as a solid, and it doesn't. Okay? So in fact, the equatorial regions of the sun rotate faster than the higher latitudes up towards the poles. So different latitudes have different rotation rates, and this is referred to as differential rotation, so this term. We'll come across various manifestations of differential rotation in this module, but this is the first one. Okay. So let me illustrate how the sun rotates. So here we have, I'm going to have a little movie showing you a speeded up version, obviously, of the sun rotating, so we can see some sunspots here. So this is from the SOHO satellite, which is mainly European satellite. Again, it's one of the links that I give on the web resources link on Minerva. So you can go and look up a lot of these cool videos on that site. Okay, so if we start playing this, you can see how the sun is rotating. So you can see the sunspot groups moving across the surface. Obviously, the rotation axis is here. You've got the sort of date and time at the top there, so you can see the days clicking over. So you can see this is quite speeded up. So some big sunspot groups coming across here now. Now, the sunspots don't last forever. They're ever changing, in fact. So even as they go across, you can kind of see them changing a little bit. If they're a big group, they will come back again. I'll just repeat that maybe. So yeah, you can see those changing there. So they sort of grow, get bigger, and then will disrupt and come back again, or disrupt and disappear. So this big group here, so you can see that a couple of weeks later, so after 2 weeks, that group will reappear over here because the big groups last for a longer time. So here they come. Okay, but they're not going to last for months and months. They will keep changing and disappearing. So the thing about differential rotation is that sunspot groups nearer the equator here will have a shorter period, maybe about 27 days or something on the equator, something like that. Whereas spots further up at higher latitudes will take longer, 30 odd, 33 days or something to rotate around. Okay, so that, and I'll give you an exercise on that a bit later to show what's going on. Okay, so that's differential rotation, which is one aspect of the sun. So it's a ball of gas, so the equatorial latitudes rotate faster than the poles. Okay, so let's get into what physically a sunspot is really going on in there. Why is it cooler? So the whole key to all of this this activity on the sun is magnetic fields. Okay, and so sunspots are telling us where there are very strong concentrations of magnetic field, where all the field lines are aligned in a vertical direction. Okay, so that magnetic field lines in a sunspot are indicated schematically here. This is a diagram from the old Seiling Gregory textbook here, but I will use some diagrams for there where they're most appropriate. And so you've got these magnetic field lines, strong vertical field here. Again, you don't need to remember the numbers here, but 0.1 Tesla is 1,000 or 10 times stronger than the Earth's magnetic field. And so it's that is key to understanding why a sunspot is what it is. And the reason that the region in the sunspot inside this vertical magnetic field is cooler is because the magnetic fields are interrupting the flow of heat from this convection flow that's going on and indicated here. here by these arrows. Okay, and so the physics here hopefully is something you've come across before. So if you think about how charged particles, okay, the surface of the sun is quite hot. There are going to be, there are going to be ions and electrons in the gas there. And so if you think about how does a charged particle interact with a magnetic field line, is the key here. And it's a basic physical principle that if you've got a charged particle coming along and a strong vertical magnetic field line here, then if a charged particle is going this way, perpendicular to the field line, then it will experience a force, a repulsive force, if you like, that pushes against the charged particle going this way. Okay? So it'll experience the Lorentz force. Whereas if a charged particle is going along a field line, it doesn't feel any force at all. Okay? So it's only when ionized plasma tries to cross a field line, that's when the magnetic field will push back against the plasma and try and slow it down or stop it. Now, because the convective flows are coming up and carrying heat with them, if you block the convection flows flowing into this region, then this region here directly below the sunspot is going to be cooler because there's not as much heat going into this region because of the magnetic field blocking the convection flow, bringing the heat in. Okay, so so that will cool it down, okay, which is why then the surface here is cooler, and therefore the spot is darker than the surrounding photosphere over here and here, which will still be up at 6,000 Kelvin. Now, because the gas is cooler, it will also be denser. Okay, so that's thermodynamics. So the denser gas will actually sink a little bit as well because it's denser than its surrounding gas. So the whole blob of cool gas here just sits lower, and so it's a few hundred kilometers lower than the surrounding photosphere as well. So you've got this dark, cool region that sits a bit lower in the photosphere, and it's all because of these strong vertical magnetic field lines. So here's a beautiful picture of one. This is a picture of a real sunspot, again, a close-up, really zooming in on one of these. Quite a nice simple one here. So you've got the umbra in the middle, that's where the real strong vertical magnetic fields, the magnetic field will be coming straight towards us here, out of the surface of the sun, or into the sun, as we'll see in a moment. And the penumbra here is where the field lines are flaring out a little bit at the edges of the sunspot, and you get this sort of, looks like a sort of beautiful sunflower type picture here. But you can see the sort of striations here. Again, that's the magnetic field lines sort of doing this on the sides. And we're looking down, obviously, from above in this picture. Yeah. Okay. Again, nice picture of the granulation again that we saw last time in the surrounding regions. Okay, so that's a nice sort of simple looking sunspot. Often, as you saw in the movie, they're a lot more complex than that, but that's a simple one. But the one thing about sunspots is that they never come alone. They are always in a pair. Okay? And that's because one thing we know about magnetic fields as well is that unlike electric fields, there are no magnetic monopoles. So basically that means that magnetic field lines kind of go on forever. They don't terminate anywhere. Okay, and so in order to get a strong magnetic field here, the most sort of stable configuration to do that is to the magnetic field lines are not going to just zoom off into space, but they turn over and form a loop like this. Okay. And so the magnetic field lines will run all the way up here and down and back into this one. Okay. So here you've got a strong vertical field, okay, with magnetic field lines flowing one direction, probably up, let's say. Whereas over here, the magnetic field lines will be flowing down, back into the sun. So you've got this loop of magnetic field. Okay. And that gives rise to what's called a bipolar pair of sunspots. Okay. So you will see a sunspot here and another one over here. And in this one, magnetic field's coming vertically out of the sun, over here, the magnetic field is going vertically into the solar surface. This loop, where you've got plasma tightly confined by the magnetic field, again, the charged particles can flow along this loop, but once they're in there, they can't really escape very easily. So the magnetic field loop basically holds the plasma in place. And it's here that you find that the plasma is already heated up to these several million degrees again. So this is, basically what makes up a lot of the corona gas that we saw at the end of the last lecture. So it can be very extended off the surface and is heated up to millions of degrees, whereas the surface here is still down at 6,000. So we can talk about the polarity, if you like, of sunspots, okay, which is to do with, it's not that the magnetic field is ending here, it will carry on down inside the sun. So the magnetic field continues, okay, so that's what we saw here, okay, so the magnetic field carries on down into the surface, it doesn't really stop here, okay, but it will loop up and around above. So we can talk about a north and a south pole to the sunspot pair that are connected by the loop, okay, and as we'll see, we can work out which direction the magnetic field is going in these loops. But you will always find basically a sunspot pair. Sometimes it can be difficult to work out what's what, but we'll see in a moment a better way to do that. Okay, so here's another image, not from the optical now. This is again from the TRACE satellite, showing an extreme ultraviolet image, so high resolution. This is the edge of the sun here, so we're sort of close up into the edge of the sun, and you can see these loops going up and down, okay, like that. And so there would be a sunspot at the base of this loop on this end, and then going over here, there would be the other end of the sunspot pair, the bipolar pair, would be on there. Okay. And similarly here, you can see more loops. Okay. So quite complex. Okay. But that's exactly what you see. So because we're looking in the extreme ultraviolet here, we're picking up emission from the gas that's from this 1,000,000 degree temperature, whereas the photosphere just appears black because it's not emitting at all of those photons. So again, the TRACE satellite has lots and lots of images like this, so it's on the web resources, so you can go and have a look at some more of these to give you a feel for what's going on. Okay, so I mentioned just now that there's a way of measuring this polarity. Okay. Let me talk about the pattern here first. Okay, so once you can reveal the polarity, a very particular pattern is noticed. Okay, so if you take a snapshot of a bunch of sunspots at any one time, obviously this is just a schematic showing you the kind of idea. So here's the rotation axis of the sun again, so spots will be rotating around like this, like I showed in the movie earlier. But if you look at the sunspots, say in the northern hemisphere, the northern half of the sun, so sorry, there's lots of north and south here, but the upper hemisphere, let's call it that, you'll find that all the sunspots have exactly the same pattern in terms of their polarity of their bipolar pairs. So let's just, they're indicated here. So that this way, all the sunspot pairs that have a loop like this would have the south magnetic pole leading them, the southern polarity spot leading, and the same here. But if you went to the opposite hemisphere, the lower hemisphere, then it would be the opposite polarity. Okay, so here the northern magnetic polarity spot would be leading the southern one. And this is very, very common. Well, this is exactly what you see. So how do we know this? Okay, so you get it from data like this. So this is another type of image of the sun, a very different one from the SOHO satellite, a particular instrument on there called MDI. And this produces a magnetogram. Okay. So what you're seeing here in black and white is basically a map of the kind of magnetic field strength in the various sort of sunspot regions. Okay. And there's a sort of a scale here. Unfortunately, this is in the old-fashioned CGS units of magnetic field strength of Gauss. So there are 10 to 4 Gauss in 1 Tesla. But basically, it's the black and white pattern here that we are interested in. So basically, anything that's white will have one polarity. Let's call it south. It doesn't really matter which it is. And then black is the northern polarity, so magnetic polarity. And so you can see, again, it's the same orientation. So this is the rotation axis. The spots will be rotating this way. And you can see that in the upper part of the sun, above the equator, then you can see this is a pair. So you have a white grouping followed by a black area. Okay? White followed by black, white followed by black, white followed by black. Okay? So all the same pattern in all the sunspot pairs in the upper hemisphere. Now if we go to the lower hemisphere, you can see the exact opposite pattern. Here, just like here, the black ones are leading the white ones, black leading white, black leading white, bit of a mess, and the black leading the white. Okay. So that's the kind of data that leads to this kind of picture. Okay. So if you're wondering where this kind of information comes from, then we'll come back to that in a moment. So here, again, just want to show another of these amazing pictures. So this is again from the TRACE satellite, now showing you the whole sun, again, showing you these loop structures. Okay, but you can see them beautifully on the edges, of course, and you can see how big they are as well. Okay, so again, there will be sunspot groupings under here. But you can just about see the idea here. Okay, so very active regions here. So you've got a loop of plasma coming up and down here. Same over here, coming up and down. So you'd know there would be a sunspot here and a sunspot here, and the same kind of thing going on up here. So that's the beauty of these multi-wavelength images. You can really probe the different types of gas. So this is probing the million-degree gas in those loops. Okay, so as promised, well, a little exercise for you at the end of this first part of the lecture. So the way that those magnetic field diagrams, the magnetograms that I just showed you, and that show you the polarity of the magnetic field and to measure the strength and direction, is measured through something called the Zeeman effect. Now, you may not have come across this at all before. So your task before moving on to the next part of this lecture is to go and have a little quick read or look up of the Zeeman effect to find out a little bit about it. It's not really part of this module, so this is more like additional learning just so that you can get a feel for how we really get the measure of the universe. Just have a little look and see what you can find, and we'll just briefly touch on it at the beginning of the next part. Both textbooks, either Caroline Osley or the Universe textbook, both have little sections at about the right level on this, using the Zeeman effect for sunspots. So those would be a fine place to go and have a quick look. Okay, I'll see you after the break.